All right, I'm hoping I can clarify some of the confusion of things that's coming up lately, because a lot of it is the binomial distribution stuff, and we haven't really talked about it yet. And so then people are like, oh, wait, what? It's this other formula? So we have another formula, and maybe that will help with some of the confusion. So the chapters have weird titles like discrete random variables and that kind of stuff. I don't need you to overly stress about it, but discrete means you can count the thing. Continuous means that it takes on all the values in between any of the numbers. So like instead of being able to go 1, 2, 3, 4, 5, continuous would be like 1.0000001 and then 1.0000002, and you can't count all of them. There's too many. They're all like way too many. So discrete means you can count it, and then continuous usually means not countable. It's got too many things in between. The particular lesson that the binomial distribution stuff comes in is under the discrete, because these are very countable things. And I'll explain what that means momentarily, but that's just vocabulary here. Binomial random variable experiments have these conditions. We'll see if I can get them all up here. These are not things you necessarily need to write down, because I'm going to guess that it was in notes you already have, but I want to kind of talk briefly about what the heck each of those things mean. In order for it to be a binomial random variable experiment, we have to have that there are identical trials happening. And when I say identical trials, I mean, like, you can't have a scenario where you had 10 things and then you pull one thing out and now you only have 9 things and then you have only 8 things. Like, it has to be the same. It has to be 10 different things each time. You can't change the parameters of the trials. They have to be the same. And each trial results in only one of 2 possible outcomes. And sometimes figuring out if it only has 2 possible outcomes is harder than it seems. And so I have a handout that has some things. We'll go through it and we'll determine whether or not this thing has 2 outcomes or not. The 2 possible outcomes, it's really weird, but they decided to call one of the outcomes a success and one of the outcomes a failure. Success doesn't mean a good thing happened. Sometimes success is you have cancer, and the failure is you don't have cancer in these problems. So success kind of gives you this feeling like it's supposed to be a good thing, and it's not necessarily a good thing. And again, that'll make more sense in a moment. When we call it a success, we usually, in this land, we call that the P. And when we have a failure, they usually call it a Q. In terms of why they chose those things, I don't know. It was random, and you could call it whatever letters you want. It's just that whenever you're looking at a stats book, usually they'll say success is the P and fail is the Q. Now, the Q is always 1 minus whatever the probability of a success is, always. And so the successes and the failure probabilities always add up to 100%. So if you have a 50% chance of a win or a success, you have a 50% chance of a fail. If you have a 30% chance of success, you have a 70% chance of a fail every time. That doesn't change. It's always got to add up to 100%. Okay. The trials are independent. And remember, our word independent means that having something happen on this one trial does not affect at all what's going to happen on the next trial. It's different than mutually exclusive. Mutually exclusive means there's no overlap on the things. Independent here just means that, let's say you get heads when you flip a coin. The next time you flip the coin, you're not like, well, I got heads last time, so it's not likely I'm going to get heads this time. It's not how it works. The coin is equally likely to be heads every time. That's independence. And then the last condition is, when we're doing these experiments, we're interested in this X. That's the discrete random variable part of this. The variable is the X, and X always stands for the number of successes out of the N trials that you're doing. That doesn't make any sense until we're looking at a problem, but we'll come back to some of that, okay? I'm gonna pass out a paper that's gonna kind of help me lead you through whether or not things are binomial or not binomial, because that matters. And so some of the problems that I've been hearing you guys kind of talk about, you might be like, I have no idea what formula we're supposed to use, and I'm instantly gonna go, oh, that's binomial. And you're gonna go, how do you know, Jen? And I'll go, because there's only two things it could be. If there's only two things it could be, then that's usually your hint that it's a binomial one. But sometimes it's hard to tell if there's only two things. We have a pencil here.
Oh, it's okay. I just don't have these things.
Oh, anyone else need the sign-in sheet? Cool, I'll put it here. So instead of making you write down all of these, I was like, I'll just print them because otherwise you got a lot of words to write. And I don't want you to have to do that. All right. Which of the following are binomial experiments? So binomial experiment means that the trials are independent. What happened in the last trial doesn't affect what happens in the next trial. And there can only be two possible outcomes. And we're going to call one of those outcomes a success and one of those outcomes a failure. Okay. So I'm going to read this scenario. Suppose 15% of the population has the Alzheimer's gene. Test 15 randomly selected patients for the gene and record the number who have it. Okay. In this scenario, you can either have the Alzheimer's gene or not have the Alzheimer's gene. There's only two possibilities. You can't half have it. You either have it or you don't. So because there's two possibilities here, and when we're talking about the entire population, I'm not talking about like selecting a person and then like needing to worry about whether I put them back or not. There's enough people in that grouping that we can assume that nothing's changing there. So this one is binomial. And if I wanted to say what's the probability of success in this case, that's the P. Success in this case means you have Alzheimer's gene. That's not a great thing to be. So success doesn't necessarily mean it's a good thing. We'd say that our P is 0.15. So then what's my Q going to be then? 1 minus 0.15, and then I heard 0.85. Both of those are correct, yes. So probability of success would be 0.15, probability of a fail would be 0.85, and then we would do other things in order to do calculations. I'm not going to actually like answer this question or anything. All right, next scenario. Asking 100 people how much they weigh. 1, rude, but 2, there's not 2 weights you could be. Like, I'm 200 or I'm 100 pounds. Like, nah, there's not 2 responses. Those 100 people are going to give you 100 different answers. So this cannot be a binomial. So just not binomial or whatever you want to say. No, not. Okay, but I encounter 100 people now and I ask them, have you ever been to Paris? And your answer is yes or no. So because there were 2 answers in this case, this one is a binomial. Now, I can't do a probability of success or a fail yet unless I have some sort of statistics on the particular group of people that I'm randomly asking. If they live in Europe, the probability of them saying yes is probably going to be a lot higher than if they live in the United States. So that's going to depend. They didn't give us any information on that here, so we would need more information to actually break this into successes and failures. Okay. Tossing a coin 100 times to see how many land on heads. Heads or not heads are really the only thing that could happen when you toss a coin, heads or tails. So in that case, it's binomial. If it's a fair coin, your probability of a success should be 0.5 or 0.50. And your probability of a fail should also be 0.5 if it's a fair coin. ABC College has a student advisory committee made up of 10 staff members and 6 students. The committee wishes to choose a chairperson and a recorder. What is the probability that the chairperson and recorder are both students? chairperson and a recorder, there are two things that they are trying to select for, but this has nothing to do with there being outcomes where when they're selecting, you're either the chairperson or recorder. So like in this whole group, you've got a bunch of chair people and a bunch of recorders, you're one or the other. Like if what they were saying is everyone on this committee is either a chairperson or a recorder and we're sort of randomly selecting that, then sure, but that's not what's happening in this case. So even though there's two things that could happen, this is not a binomial. Roll a fair six-sided die 20 times. Record the number of times that a 2 comes up. This is hard, okay? My gut tells me when I roll a six-sided die that that's not two things happening, but what am I recording? If it's a 2, and if it's not a 2. So this one is binomial because the only two outcomes I'm recording are, is it a 2 or is it not a 2? So this one feels like a trick. It is binomial. Tyler makes 70% of his free throw attempts. Apparently this is a basketball thing. Suppose he makes 15 attempts. So he throws the basketball 15 times and tries to get it into the basket. I'm saying these words because I am not a sports person, so sometimes people need these explanations. He's trying to get them in the basket. He makes 70% of the ones that he usually tries. Record the number of baskets that he makes. So what can happen if he throws it? He either doesn't get it in or he does. So this one is binomial. And actually free throw problems are like classic binomial problems. They like almost always come up on homework or exams. A lacrosse team is selecting a captain. The names of all the seniors are put into a hat, and the first 2 that are drawn are the captains. The names are not replaced once they are drawn. No, so even though we still had 2 that we were pulling, that had nothing to do with there being 2 outcomes that could happen. So this one's not binomial. So there was a homework question I heard people talking about that had to do with probability that you have a girl. This is now stupid because in the real world, you could like have not a girl or a boy. But back when they wrote these stupid textbooks, there were 2 choices. You either have a girl or you have a boy. They only went with 2 genders on these things. So that those questions are intended to be binomial questions. If they're saying probability you have a girl, they're basically like, well, if it's not a girl, then it's not a girl or a girl. You have 2 probabilities. So homework questions like that, if you're looking at them and there's 2 things that could happen, they're probably going to be using the binomial formula, which we haven't gotten to yet. That's down here. Yes.
Should we assume that it's not binomial when it says like not replacing like certain stuff?
So there's other distributions that are in these chapters that have to do with what happens if you don't replace the thing, if there's not very many. When we're in a big giant population, if we're talking about the United States and I select a person, I'm technically not going to select the person again. So I'm really not replacing them. But in a large scale, we can assume that that doesn't matter. But if I'm doing the exact same experiment, so let's say I'm coming back up here to this and the population that I'm talking about a really small group. And I'm not randomly selecting if I'm actually pulling someone out of the group. If I'm asking among 3 people and you pull someone out, then the probability that you're going to choose one of the remaining 2 people is way higher because there's no one in that group. But if it's a bigger group, then we don't have as big of a problem. That will come up later. For right now, if they haven't talked about the Poisson distribution and all the other ones, then don't worry about those words. They're later. There's a hypergeometric distribution and they often skip them as well. So we'll see what your professors choose to do. For now, here's some notation. If it's a binomial problem and they ask you to write the distribution using the proper notation, that usually freaks people out and they're like, what does that mean? It literally means you're going to put a big ol' X that's standing for your random discrete variable. You're going to put this little squiggly thing. I'm sure it has a name. I haven't looked it up. I call it a squiggle. If it's binomial, you put a big old capital B there. And then the N is how many the thing is out of. And the P is the probability of a success. So if I went back up to our very first scenario up here, where we talked about 15% of the population had the Alzheimer's gene. If I wanted to write what that distribution looked like, I would put a big capital X, I'd put the little squiggly, I'd put a capital B there, and then they want me to put the N next. The N is out of how many people am I talking about? 15. Because it said 15 randomly selected patients. And then comma, I want to put the P down. The P we said was 0.15. Would have been good if I had made a percentage that didn't look like it was that. That 15 has nothing to do with that 0.15. That 15 has to do with the number of people. That's my N. And the 0.15 is coming from the probability of a success. Yeah. So that's all that notation means. I don't want the notation to freak you out, but when I see it sometimes I'm like, ugh. So it's always N, comma, whatever the probability of a success is. I already heard people talking about, the mean and the standard deviation are different in this section. Yes, if we're talking about a binomial distribution, then your mean is going to be N times whatever your P is. So in the last problem that we were just talking about, you would say 15 times 0.15, and that would be your mean on this one. That's all. And then when they want the standard deviation, you put the N and the P, and then actually 1 minus P. Remember, that's always Q. So sometimes people will write this formula as the square root of NPQ instead. They mean the same thing because 1 minus P is always the same thing as Q. All right, and then here is the terrible looking formula. It looks really scary. This N and X here inside that's a combination. You've learned combinations already. So this says combination N choose X. You're going to raise the probability of a win to the power of whatever the heck that thing is. And you're going to raise the probability of a failure to that number minus that number for your power. It's a weird formula. It's not hard. And both classes get some kind of formula sheet, so it's not a thing you have to memorize. But when you do a bunch of homework problems on this, you'll memorize it eventually because you'll be like, I've done so many of these. So just a reminder, in this notation, that means combination. And so it means put the top thing in the top, put the bottom thing in the bottom, and then that thing minus that thing inside parentheses and put the factorial after. That's our combination formula. You've already seen the combination formula.
What does the X stand for?
The X is going to stand for, so like, let's say from the probability problem that we had up at the top where it was talking about 15 people were selected. If I was saying test 15 randomly selected patients and give the probability that exactly 3 of them have the Alzheimer's gene, you'd put 15 in the top and you'd put 3 for the X. So the X is what's the probability of the thing I'm asking you for. It'll make sense in just a second. All right. The questions are not long. I put explanations below the questions. So all these words are things that you can go back and read later. Don't worry about it. I'm going to talk through it. But if later you're like, what did she say? I wrote the words out. So that's all there in language. Okay. So here is a scenario where we would use this formula. A company has a fleet of 50 trucks, each of which has a 10% chance of breaking down on any given day. Guess what our success is? That the truck breaks down. So again, success is not like a good thing necessarily. So my P in this problem is 0.1 or 0.10. Totally cool if you want to write it with the 0 so that you can still feel the 10%. It feels sometimes more natural if you have it like that. You don't have to though. Probability of success is 10%. So what's my probability of a fail? Yeah, it's 90%. It's always 1 minus whatever your probability of success is. Okay. What is the probability that on a given day, at least 5 trucks will break down? Okay. When we do the formula I showed you, so the formula wants you to put N on the top, X in the bottom inside the parentheses. That's the combination, N choose X. Then they want the probability of a win raised to the power of that X, or success. Sorry, I keep saying win. Then they want the probability of a failure raised to the power of N minus X. That's the formula. And I'm going to write something and I'm going to explain to you why this is not the answer. We have 50 trucks and they want at least 5 of them to break down. The P is 0.10 raised to the power of that 5. And my loss is 0.90. You don't have to write the 0 out front. It's just sort of my habit. I usually do. Raised to the power of 50 minus 5, so 45. And we can do this whole calculation. The actual calculation of the thing is actually often not what your professor wants. They often just want you to be able to put it into the formula, and I'll show you why in just a second. This is not the answer to the question. This is the answer to a slightly different question. So, see how it says, what is the probability that on a given day, at least 5 trucks will break down? What I just answered you, if I took this and I actually calculated out, this is the probability that exactly 5 trucks will break down. If I want the probability that at least 5 trucks will break down, I have to calculate this. Then I have to do it again for 6 trucks. Then I have to do it again for 7 trucks, 8 trucks, 9 trucks, 10 trucks. When do I get to stop, Jen? 50 trucks, because you have to go all the way up to N. Oh my God, you're not going to do that. The nice thing about learning about complements is that answering the question for at least 5 trucks is the same as answering the question for fewer than 5 trucks if I subtract that number from 1. Because out of 100% of the things, if I calculate the opposite of what they asked for, 1 minus the opposite of what they asked for is the answer you want. I would much rather calculate for you the probability that no trucks broke down, 1 truck broke down, 2 trucks broke down, 3 trucks broke down, and then 4 trucks broke down. Because if I add those up and subtract that from 1, that's going to give me the same thing as if I did 5, 6, 7, 8, 9, 10, all the way up to 50. I would really rather do 5 calculations than 45 calculations. But that's what gets to be a little bit tricky about these. If I put this in, this is the probability that exactly 5 trucks. So that's not what I want. What I really want is I'm going to instead calculate the probability. And what they do with these probabilities is they'll put that X is the random variable. If I wanted it to be at least 5 trucks, so up here, what they were actually asking you for was the probability that X is greater than or equal to 5 is what they really wanted from you, because at least 5 trucks means 5 trucks or more trucks. But instead, we're going to calculate the probability that X is less than 5 and subtract it from 1. That's called the complement. Okay. Now, all these paragraphs that are right here down below, that's what I just said in words where I was explaining I would rather not do. Blah, that's all there. So if you read it later, hopefully it still makes sense. Okay. Now, to actually do this calculation still requires you to add up the probability no trucks, the probability of 1 truck, the probability of 2 trucks. So you're going to calculate the probability that X is equal to no trucks breaking down plus the probability that X is equal to 1 truck breaking down plus the probability that X is equal to 2 trucks breaking down plus 3 trucks breaking down, and then 1 more plus 4 trucks breaking down. And then you're going to do 1 minus all of that. So I suppose I could put that whole thing in brackets and do 1 minus that thing. So often in the actual tests or quizzes or whatever, they don't want you to, because this still, you're going to have to go do this style calculation to get that, and then do it again with a 1 and do it again with a 2 and do it again with a 3 and do it again with a 4. That's a lot. So often when they're actually asking you to answer these, they want you to write what I just wrote here and not actually do the calculation, because they're like, I want to know, do you understand how to get the answer? I don't necessarily care that you got the answer. Why is that the case? Because in the classes where you're allowed to use the graphing calculator will actually do this for you. In the class where you're not, you have to do the whole dang calculation. So people who have the option of using the graphing calculator, you're never actually having to go through and do any of the actual crazy calculation, but you still have to understand this or you're going to get the answer wrong. They may have also talked about a table. And the table has the answers to all of these things in here if you know how to read it. Did they show you like you could use a table and say that was okay for the homework? That's nice, because then you don't have to do the calculation, but you do have to understand how to read the table. Do you want me to show you how to read the table? Okay, so let's say I want the probability, let's see, does this one go up to high enough? Doesn't go up to high enough for our 50 problem. So we would need a table that would go up to 50. So let's pretend like this didn't say that there were 50 trucks in there. Let's say it had 10 trucks in there. If it had 10 trucks, then what I would be doing is looking for the p-value that we had in the problem. And we had 0.10. So along the top, I've got a 0.10 right there. And then in terms of the X, I got to go find 10 if I decided I was doing it for 10 trucks. I got a 2, a 3, a 4, a 5, a 6, a 7. So I'm not on the right page. I would have to go to the next page. The chart I have only goes up to 20. So we can't do 50, but I can do 10. So then we would go down to 10. I'd stay underneath the 0.1. And then off to the side on the 10, this would be the probability that 0 trucks broke down. This would be the probability that 1 truck broke down. This would be the probability that 2 trucks broke down. And we would add all those things up. The number I've got on this problem is too big. It's a 50. So they would have to give you something that would fit on the table. So I would assume if they're giving you the table to use for a quiz or a test, they've given you a table that has the correct numbers on it. And they're only designing problems that will let you do that. So the table can help you find the probabilities. But without the table, we can still do the math. And so I'll go through one where we actually do a calculation where we don't have to do an insane number of math in order to get it. Okay. So I'm trying to think. Let's go ahead. I'll set up the second one and then we'll do an actual problem. A factory produces bolts at a defect rate of 2%. What is the probability that a sample of 100 bolts will contain at least 3 defective bolts? So defective bolts, that's actually a win or a success in this case. So my P here is going to be 0.02. So probability that my bolt is defective is my success. Q is probability that my bolt is not defective, which is going to be 0.98. In this problem, my N is 100, because they said out of a sample of 100 bolts. And my X in this case is going to be 3, because it says, what is the probability that of a sample of bolts, 100 bolts will contain at least 3 defective bolts? So X is equal to 3, but then what else is my X? Up to all 100 of them. They're asking you, what is the probability that there's at least 3 defective bolts? So there could be 3 or 4 or 5 or 6 or 99 or 100 defective bolts. So again, I don't want to answer that question. I want to answer the probability that there are fewer than 3 defective bolts. So it's easier. So the question actually wants you to find the probability that X is greater than or equal to 3. That's the actual question. It's going to be easier for us to answer 1 minus the probability that X is less than 3. And in terms of what would that calculation look like for you, then that means you need to calculate 1 minus the probability that X is equal to 0 defective bolts plus the probability that X is equal to 1 defective bolt plus the probability that X is equal to 2 defective bolts. So we would have to do 3 of those calculations, but that's not really that bad. So if I want to do probability that X is equal to 0, then this one is going to be 100, choose 0. My probability of a success is 0.02. And we raise that to the power of that X. So that would be to the power of 0. And then my probability of a fail is 0.98. And we raise that to the power of 100 minus that X. So that would just be 100. So you would calculate that. Then this one over here is 100, choose 1. And you would do 0.02 raised to the power of 1. And you'd do 0.98 raised to the power of 100 minus that 1. So it would be to the power of 99. And then we would do one more of those crazy calculations. And you do 100, choose 2. And that would be 0.02 raised to the power of 2. So it's always raised to that power. And then 0.98 raised to the power of 100 minus 2. So that would be 98. So in your calculator, you'd figure this out. And then you would add it to these other 2. And that whole thing, you're going to subtract from 1. So you'll take 1 and then subtract those 3 calculator parts. Often, this is the answer that your instructor wants. They don't necessarily need you to do that calculation. It just depends. So you just have to ask what it is that they're looking for. And they usually are pretty clear, like leave it like this or do the actual calculator part. In terms of doing the actual calculator part, it's you doing your combination formula, and then this to the power of 0, anything to the power of 0 is just 1. And then you put 0.98 in your calculator and raise it to the 100th power, and you would multiply those 3 things together. So they're not really terrible to do. They just look terrible. They look awful. Okay. So let's look at one of your actual, well, one of the class's actual homework questions. Use the following information to answer. Can I make it bigger without it falling off the page? Almost. There we go. Use the following information to answer the next three exercises. The probability that the San Jose Sharks will win any given game is 0.3694. That's our probability of success. There's our P. That's over a 13-year history of 382 wins out of 1,034 games played, and it says as of a certain date. An upcoming monthly schedule contains 12 games. The expected number of wins for that upcoming month is what? So we've got some interesting letter choices off to the side. What this is asking you to do in terms of you having a predicted win total, you had 382 wins out of 1,034 games. If you take that number, 382 divided by 1,034, that's where that 0.3694 number came from. So you don't have to stress about the, like lots of people stare at those numbers and are like, what the heck? What am I supposed to do? We'll go, well, they already actually gave you that. That was redundant information. Okay. Expected number of wins for the upcoming month. Okay. We've got 12 games planned for the following month. All right. Let's look at this part isn't necessarily asking you to do anything crazy yet. Down here is where we're going to actually start using our formula. If you've got a probability of 0.3694 chance of winning and you've got 12 games coming up, you want to take the 12 and you want to multiply it by that 0.3694. Okay, so let's look. 0.3694 times 12 is going to give us 4.4328, which is not exactly any of the answers, but when they round it, that would be that. So you haven't used the formula yet. This is just asking out of all of the games, what's the probability that we should be getting wins? We should get 4.4 wins. What's 0.4 wins? This is how probability works. You don't necessarily have exact numbers here. But now, here's where our formula starts to come in. What is the probability that the San Jose Sharks win 6 of the games in the upcoming month? Win 6 games. It does not say win greater than 6 games. It does not say less than 6 games. It says they win exactly 6 games. So this is your X. X equals 6. Okay. Our N in this problem is the total number of games that they play in a month. And they told us they play 12 games in a month. Our probability of a win was 0.3694. So we have to figure out what the probability of a loss would be, or a failure. So that's going to be 1 minus that. 1 minus 0.3694 is 0.6306. And now we have all the things that we need. So we're gonna take 12, that's the n. We're gonna put the 6 down below it. So we want combination 12, choose 6. Then we're gonna put the probability of a win, so 0.3694. And what do I raise that to the power of? 6, so it's whatever that number is down there. Okay, and then we're gonna multiply by the probability of a loss, 0.6306. And what do I raise that to the power of? So it's actually 12 minus 6, which is just 6. So that's the calculation we've got to do. Okay. This part right here, that's me doing my combination calculation. So that's going to be 12 factorial over 6 factorial times 12 minus 6 factorial. And then 0.3694 to the power of 6. Is approximately 0.00254 1. I'll call that good. And then the other one, 0.6306 to the power of 6. To the power of 6 is approximately 0.062882. I'll call that good. All right. So I got to do my factorial calculation. So that's 12 factorial over 6 factorial times 6 factorial. Okay. So 12 factorial over 6 factorial is going to give me 12 times 11 times 10 times 9 times 8 times 7. And then I cannot write the 6 factorial that's right here, because I can cancel it, but this one will be 6 times 5 times 4 times 3 times 2 times 1. And then we're multiplying by those two things. So that'll be 0.00254 times 0.062882. 0.000159. Cool. So once I do that and then I do that calculation, I should have my answer. And let's see. Ten times, nope, 12 times 11 times 10 times 9 times 8 times 7 is equal to 665,280. And then 6 times 5 times 4 times 3 times 2 is 720. So that's 924. Okay, so this part I want to multiply. $924 times that crazy decimal. 0.0001598. Okay, so I got 0.1476. Okay, and looking at our answer choices, whew, that would be answer choice A. So these calculations, like when they actually want you to do the calculation, if you only have like a regular scientific calculator, these can really suck. If you have the scientific calculators that already do the factorials for you, that's way better. So I would find a friend if they have a calculator that has the factorial button in it, because you see how much more you have to write if you actually have to do that part of the math. And if you've got a graphing calculator and you're allowed to use it, it will do the entire calculation for you. You just have to enter it in there. And if you want me to show you how to do that, come to office hours and I'm happy to show you how to enter the things in your particular calculator. All right. I hope that helped a little bit getting you into the, like, what the heck you're doing with the binomial stuff. It's mostly trying to identify in the problems. You need to know what the N is, the X is, the P, and the Q. And if you can do that, then the next hardest part is figuring out, are they asking me for exactly something? So like in a problem where they're asking you, out of a family of 5 children, what's the probability exactly 3 of them are girls? That's one calculation. If they want the probability that you have at least 3 girls, then you have to do 3, 4, and 5. If there's 5 children in the family, you have to add those up. So sometimes you have to figure out, is it easier to do a complement of the actual thing versus the actual calculation? All right, I'll end it there.